this is really kind of an overview of statistical learning methods and how does it relate to the computational methods we have discussed for the rest of the semester. And so for the rest of the class, I want to spend some time reviewing what we have learned in this semester. Before that, I want to see if there are any questions about this part we have just discussed.
Is the lecture from Monday online yet?
It's being processed right now. I should post it this afternoon.
Great, thanks.
Mm-hmm. Any other questions? All right. So let me go to our review part. I want to spend like 30 minutes to review what we have learned. Okay. So we'll start from the ordinary differential equations. So these are the things you are expected to have learned during this semester's study. What are some common schemes for solving ODEs, right? Things like forward Euler, backward Euler, trapezoidal rule, midpoint, and some really elementary, simple Runge-Kutta schemes are the things we are looking for. And basically, what are their formula, right? So basically, given a name, you should be able to remember what the formula is for these very simple schemes. And for Runge-Kutta schemes, I mean, if you know Runge-Kutta 2, it's probably good enough. And the more complex Runge-Kutta schemes, nobody actually, I mean, very few people actually remember them in their head. But like you can just look over Wikipedia to get the coefficients. But still, knowing the concept is the important part, right? So if you look up over the coefficients on Wikipedia, you should know how to implement them. Now, how to analyze the local and global order of accuracy. So this is related to how to do Taylor series analysis, right? How to figure out how many orders to expand, right? You need to expand until to sufficient order so that you actually get what is the leading truncation error. Okay. So what is the zero stability and eigenvalue stability? Again, zero stability means if you solve the equation, du dt equal to 0, right? You have no right-hand side. Is the scheme stable? A lot of schemes are not even stable, solving du dt equal to 0. So if that's the case, the scheme is probably useless, right? So it's really the really necessary condition for the scheme to be of any use. Eigenvalue stability is different. Eigenvalue stability relates to how do you solve du dt equal to lambda times u, right? And a scheme may be eigenvalue stable, maybe not eigenvalue stable, and it usually depends on the combined parameter w times delta t. So this is the key parameter that is going to determine if a scheme is eigenvalue stable or not eigenvalue stable. And that links to the stability region of a scheme. A stability region of a scheme can be either plotted in terms of a real of lambda and the imaginary part of lambda, or sometimes it's plotted as a real and the imaginary part of lambda times delta t, right? If it's plotted as a real and imaginary part of delta t, the advantage is that you don't have to scale the stability region bigger or smaller if delta t is bigger or smaller. It's going to be a fixed plot. Or you can think of this is a stability region when delta t is equal to 1, and the region would expand in proportion to 1 over delta t. Okay, so we learned the stability region of forward Euler, something like this, right? Centered at -1 and extends to -2. So that's forward Euler. And we also learned backward Euler. It's a circle on the right, However, it is not stable inside the circle. It's stable outside the circle, right? So that's a backward Euler. For forward Euler, the stability region is inside the circle. Okay, and some other schemes you should look up for is the midpoint is going to be strictly on the imaginary axis over here. Trapezoidal rule. Trapezoidal rule is the entire left-hand side, right, including the including everything that is stable for the original ODE, and not including anything that is unstable for the analytical ODE. Okay, and Runge-Kutta schemes have weird shapes in its stability region. Excuse me. And the RK2, for example, has a stability region that's kind of like a deformed oval. So basically, you should roughly know where the stability regions are for simple schemes. Okay, so what is a stiff system? A stiff system is basically a system of equations with vastly different eigenvalues. Some eigenvalue is much larger, let's say 1,000 times larger than other eigenvalues. And it is important in deciding what kind of scheme to use. For any explicit scheme, the time step size, delta t, applied to an stiff system would be restricted by the largest eigenvalue, while the length of the time integration has to be inversely proportional to the smallest eigenvalue, because that determines the time scale of the system. That means you have to spend a lot of time steps, right? So a stiff system usually leads to the choice of a implicit integration schemes. So that's really the pro of an implicit scheme. Of course, the pro of an explicit scheme is that it's much simpler to implement. You don't have to solve any equations, right? I mean, just you have to evaluate the explicit formula, but you don't have to solve a linear or nonlinear system. And if you use an implicit system and solve a nonlinear system, we have studied the Newton's method of solving these nonlinear equations. So that's the ODE part of the class. Any questions for the ODEs?